Let me welcome you all to a new edition of Physics. In this edition, we'll learn about electromagnetic induction. What is electromagnetic induction? We'll learn about Faraday's law, Lenz's rule, Professor Fleming's right hand, and the difference between Fleming's right hand and Lenz, how to use each one of them. And also we'll learn about mutual induction. Before we start, let me remind you, please note you can follow us on the YouTube and you can watch the episode over and over again on the educational channel. So let's get started. Chapter 3, Electromagnetic Induction. Okay, we'll start with the definition of electromagnetic induction. It is generation of an electromotive force in a conductor. By the way, conductor means a straight wire or a coil, circular or solenoid, as a result of the variation of the magnetic field intercepting the conductor. So the definition of electromagnetic induction, it is generation of electromotive force in a conductor when this conductor is exposed to a changing magnetic field. Okay? Faraday's experiments. Here in front of you, we've got a coil, and we've got a solenoid, okay, and it is connected to, the coil is made of many turns, a coil of many turns, and it is connected to center zero galvanometer. Center zero galvanometer, and a magnet is held at rest close to one end of the coil. Your attention, please. The magnet is stationary. It produces magnetic field, and some of the field intercepts the coil. But as long as the magnet is stationary, is held at rest, the field that intercepts the coil is not changing. Okay? A magnet is held at rest close to one end of the coil, and no current is observed to flow in the coil. Why? Simply because the magnet is stationary, and the galvanometer, it is, yes, center zero galvanometer, the pointer is at the center, it shows no deflection. So we don't have any current, though we've got a magnetic field that intercepts the coil, but it's not changing. Okay, this is very good. Talking about the experiments of Faraday's. And now the magnet, yes, is plunged into the coil. The magnet is moved towards the coil, and the galvanometer needle swings to one side, indicating that a current is flowing. Your attention, please. The current, yes, is flowing, and it will flow just as long as the magnet is moving. Okay, while the magnet is moving towards the coil, the field intercepting the coil is changing. Actually, it is increasing. As long as we've got increasing magnetic field, we'll have, yes, electromotive force and a current will flow. And this happens when the magnet is moved towards the coil. The galvanometer shows deflection on one particular, yes, side. Okay, your attention now. The magnet, the same solenoid, but now it's not moving towards. We'll move it away from, yes, what will happen? Yes, on removal of the magnet away from the coil, the needle deflects also, but in the opposite direction. It deflects in the opposite direction. Deflects means we've got electromotive force and a current flows. In opposite direction means that, yes, the current reverses its direction. The question is why? The magnet is moved away. Yes, we've got a changing magnetic field. It increases or decreases as long as we've got a changing magnetic field. The only thing that differs, the direction of the current. When approaching, it shows the deflection in one particular direction. On removal, it shows deflection in the opposite direction. In both cases, we've got a changing magnetic field intercepting the coil. It is increasing while the magnet is moving towards the coil, or it is decreasing while the magnet is moving away from the coil. By the way, we can make the magnet, we can hold it at rest, and we move the coil towards the magnet or away from it, and we've got the same observations. Okay. And now, the needle swings further, indicating that the EMF induced is increased. Now we've got something very important. How to increase the current? How to increase the EMF induced? Okay, deflection increases means the current induced is increased. The deflection is increased when the experiment is repeated using a coil of many turns or more turns. And this is very important. So the experiment is repeated using a coil of greater number of turns. And what happened? Deflection, the swing of the needle is increased, and deflection is increased, EMF is increased. So what conclusion can be drawn from such a thing? Yes, EMF is directly proportional with the number of turns on the coil. EMF induced is directly proportional with the number of turns on the coil. Okay, EMF is increased when something very important. We are repeating in the experiments and we're doing some changes, and we've noticed that the EMF induced is increased when a soft iron core is placed inside the coil. Okay, so keeping the same coil, but we've placed a soft iron core inside it. Deflection is increased. Experiment is repeated using a stronger magnet. Also will increase the deflection, will increase the EMF. And experiment is repeated using a coil of the same number but of greater area. And what conclusion can be drawn from such a thing? Okay, experiment is repeated and the magnet is moved faster to the end of the coil. In all these cases, deflection is increased. So we repeated the experiment using a coil of greater number of turns. And the swing of the needle of the galvanometer, deflection is increased. And this indicates that the EMF is increased. So we draw a conclusion here. EMF is directly proportional to the number of turns. The greater the number of turns, the higher the EMF is induced. But we've got something very important. We repeated the experiment with, yes, a stronger magnet. Stronger magnet will produce, yes, a stronger field. We repeated it with placing a soft iron core inside the coil. This will concentrate the field inside the coil. We repeated it with a coil of greater area to receive more and more flux lines. Okay, and all these things, in all these experiments, the deflection is increased, EMF is increased. So we can say EMF is directly proportional to the change of the magnetic field. But something happened, okay, very important. When moving the magnet faster, deflection is increased. So EMF is not only proportional to the change in field, but rate of its change. It depends on rate of its change. Moving the magnet faster means it takes shorter time. Okay, so EMF depends on delta phi change in field, and is inversely proportional to the time, rate of change in magnetic flux. So EMF is directly proportional to the rate of change of magnetic flux. So we've got now two conclusions. First of all, EMF is directly proportional to the number of turns, okay, and EMF is directly proportional to the rate of change in the magnetic flux linking the coil, linking the conductor. So we can say EMF is proportional to N delta phi over delta T. Proportionality sign is replaced by equality as usual, and we expect to, put a constant. Constant equals 1. So EMF equals, N delta phi over delta T, but a negative sign here appears, and it has, a great significance. It means, the negative sign in the previous relation indicates Lenz's law. And we'll explain Lenz's law. So EMF is directly proportional to the number of turns. The greater the number of turns, the higher the EMF induced. EMF is directly proportional to the change in the field. The greater the change in the magnetic flux, the higher the EMF induced. And it is inversely proportional to the time of that change. So it is proportional to the rate of change. Combining both equations, EMF equals negative and delta phi over delta T. Negative sign here has a meaning. It indicates Lenz's rule or law. So let's learn about this law. What about Lenz's rule? Lenz's law states that the direction of the induced EMF is opposing to the change producing the induced current. Let me say it again, the direction of the induced EMF is opposing to the change producing the induced current. Okay, I'll explain it. Don't worry. It's all easy and you will find it very interesting. Okay, what we've got here, we've got a magnet. Your attention. The pole, nearer to the coil is the North Pole. Okay, the magnet is plunged into the coil. What happens? When the North Pole of the magnet is pushed into the coil, the induced current flows in a direction. It chooses to flow in a direction such as to oppose a North Pole. Okay? When approaching North Pole, we expect to find a North Pole at the close end. At the end of the coil facing the North Pole of the magnet. This happened when approaching the North Pole. And if we repeat it and we approach the South Pole, also we'll expect to find S pole, South Pole at the end facing the magnet. Okay, and now what if the magnet is pushed away, is pulled away, or removal of the magnet? What happens? The current is reversed. Okay, North Pole is moved away, a South Pole is produced. When the North Pole is pulled away from the coil, the direction of the induced current is reversed to produce, South Pole. Okay, in this case, the change producing the current is the withdrawal of the North Pole. So the current will oppose the withdrawal of the North Pole by producing S pole, South Pole, to attract it. It opposes withdrawal by producing South Pole, a like pole, to attract it. In the first case, the current is produced due to the approaching of the North Pole. So the change producing the current is the approaching of the North Pole. the current will oppose the approaching of the North Pole. Okay, how? It will produce a North Pole near the end, close to the North Pole. So what about Lenz's rule? It states that the direction of the current, or whenever an EMF is induced, the direction of the current must be in a way such as to oppose the change producing it. Okay? Let me explain it. Let me simplify it. In all cases, the current opposes motion. In all cases, the current opposes motion. Okay? When the North Pole is pushed by producing, yes, unlike pole. Okay? So in all cases, you will notice that, please note that the current opposes motion. Let me say it again. North Pole is plunged into the coil. This is the change producing the current. So the current opposes it. It will produce North Pole to repel it. North Pole is pulled away. So what is the change producing the current? It is the removal of the North Pole. Okay, it is the removal. It won't allow it to remove. It will produce S pole to attract it. If you think about it, you will note something very important. The current opposes motion. So when the current, by the way, let me remind you something. When the current flows anti-clockwise, it produces North Pole. Yes, clockwise, it will produce South Pole. Just to remind you of this important piece of information. Okay. So we've got here something very, very important, and it is a major difference between Lenz's law and Professor Fleming's right law. Lenz's law or rule determines the direction of the induced current in a coil, but Fleming's right, yes, in a straight wire. So let me stress on it. Lenz's law determines the direction of the induced current in a coil. Determination of the induced current in a straight wire. A straight wire will use something else. We'll use Professor Fleming's right hand. Fleming's right hand rule. Okay, what about it? The statement of Professor Fleming's right hand. It states that if the first 3 fingers of the right hand are held at right angles to each other, with the 4-finger pointing in the direction of the field. So first 3 fingers are held mutually perpendicular, held at right angles to each other, yes, with the 4-finger pointing in the direction of the field, thumb in the direction of motion, 2nd finger, yes, points in the direction of the induced current. This rule is used, this law is used to determine the direction of the current in a straight wire. Don't ever forget, Lenz's rule is used to determine direction of the current in a coil, but Professor Fleming's right hand to determine direction of the induced current in a straight wire. We'll take some examples. Okay, once again, here the right hand with the first 3 fingers held mutually perpendicular at right angles to each other. Okay, 4-finger field, thumb pointing in direction of motion, then the 2nd finger, the middle one, will point in the direction of the induced current. Okay, we've got something very interesting here to remind you with the rule. Okay, once again, your attention please. First finger. Okay, finger, first finger, F stands for field. First, letter F, and first finger stands for field. Okay, thumb, your attention. Letter M, Yes, just to remind you, with the thumb pointing in the direction of motion, and second, C in second reminds you with current. Second finger, C in second finger, yes. So the second will point in the direction of the current. Okay, so it's all easy. You can remember it. And now we've got, yes, a magnetic field from the north to the south. This is the direction of the field. And we've got a wire, and of course the wire is part of a closed circuit. It's not shown in front of you, but we expect you to know this quite well. And this is the wire. The wire should be moved to change the field so as to produce electromotive force and current flows when the circuit is closed. Okay, here is motion. In what direction will the current flow? Try to do it yourself, please. In front of you, we've got, yes, two known things. Direction of field is from the north to the south. Direction of motion is shown in front of you. It's upward. Now, in what direction the current will flow? Okay, in this direction. How? We'll use Professor Fleming right hand. Okay. Thumb pointing in direction of motion. Thumb pointing upwards. Forefinger points in direction of field. Thumb, yes. So second will give the direction of the induced current. We'll make a little bit of a change to make it a little bit more difficult. Okay. I think it is quite clear. And now we reversed the field. Field is from the north to the south. Okay, this is the direction of the field. And we've got a wire, and the wire is moved, yes, downwards. In what direction will the current flow? Okay, try to do it. I know it is a little bit more difficult. Use your right hand. Okay. In this direction, it will flow in this direction. Once again, yes, you have to modify the position of your right hand. Forefinger field, thumb motion. The current will be given by the second finger. It is outwards, out of the screen. So we've learned about Lenz's rule and Professor Fleming right hand. And now it's high time to make a comparison between, yes, Fleming's left hand rule and Fleming's right hand rule. Okay, it is applied about Fleming's left hand rule. Your attention, I'm comparing between Professor Fleming's left and right. We've used Fleming's in the magnetic field of electric current, chapter 2. Yes, it is applied when a current causes motion. A current, yes, first we've got a current is allowed to flow, then motion appears, is produced. So we think about Fleming's left when a current causes motion. Fleming right is applied when motion, we start with motion, and motion induces current. Your attention. We moved the wire, yes, between the two poles of a magnet, and a current is produced. This happens with Fleming right. But if a current is allowed to flow and motion occurs, now this is Fleming left. Fleming's left is used to determine direction of motion, but Fleming's right is used to determine direction of the induced current. And this way we've come to the end of this edition. Until we meet again, my best wishes to you all. All the best for you. Stay safe. Goodbye.